Okay, let's see if this video will run for me. I'm gonna make this happen. So it's putting an ingot in the one side of the machine. It's then going to reverse robot position, remove the part from the previous shot. Right now it's picking up another ingot for the next cycle. So for 27 years in the MIM industry, I was asked repeatedly, so how do you get the stainless steel so hot before you inject it into molds? And of course, for those of you that are familiar with metal injection molding, the metal itself does not become viscous, it's not heated, it's the polymer binder system that carries that metal powder into the mold. So very different approach. I never thought I'd actually be involved with the technology where I could say we were melting the metal before injecting it into a tool. So what's our relationship with Engel? Actually, we have two real important relationships. One on the alloy side. So Materion is our material supplier. If you're interested in making parts, you can get a license from LiquidMetal, produce your own, buy material from Materion. I believe they're about a $2 billion material supplier. They're in Ohio. And then, of course, injection molding equipment exclusively from Engel. And it's been a great partnership, and we're excited. This is a big year, I think, for both businesses with the introduction of our current equipment technology. We do have a contract manufacturer that we work with, and we hope to expand those relationships. So if you're interested in getting parts made, we can help you do that as well. Our facility in Rancho Santa Margarita, California will principally remain an R&D center, prototype and pre-production, kind of get programs launched and then transition to a contract manufacturer. So some design criteria for the process. Part sizes up to about 80 grams. That's our current limit of technology. Minimum radii of 0.2 millimeters is typical. This process does require draft. The material shrinks about 0.2%. So if we don't have draft both on outer and inner features, we've got a real problem. You've got a straight wall tool, you're going to mold a part and it probably won't come out. And you remember it's RC54 hardness, so you've got a real mess on your hands if the tool's not properly designed. Ideal wall thicknesses, about 1 millimeter to 4 millimeters. We can go a little bit below the 1 millimeter mark, but that's kind of our sweet spot. And then ejection, we use standard ejector pins and blades common to plastics. So how does it compare, and really where would you use it? So the first piece I described as amazing dimensional accuracy. We're seeing part accuracy, part after part accuracy and repeatability indicative of the quality of the mold. The shrinkage is very little, 0.2%. So it's amazing precision when you compare that to technologies like metal injection molding, which have a whole series of conversion steps. You're compounding feedstock, one grade source for variation, you're injection molding the material, then you have to debind it, then you have to sinter it, and then if you're sintering, of course, the material shrinks 20%, so you're fighting the effects of gravity, friction on the setters that the parts are sitting on. All those things influence the dimensional results. And by the way, I'm not pitching this as a replacement for MIM, it is not, but it does have, I think, a special place for high precision medical components. The surface finish I've mentioned already is just really incredible, at less than 2 RA micro wrench. Again, it reflects the finish of the tool, so if you want textured surfaces, you need to put that on the tool. That's what you'll see on the finished parts. And like all technologies, I think LiquidMetal process has unbeatable economics. One of the individuals at LiquidMetal was talking to me the first week of working there, and he said, you have to be ready because our process is kind of expensive. But I find that's only true when you're improperly applying process technology to a product application. I'm a believer, and I've said this my whole career, that parts find their way to the right process. If you put them on the wrong process, it won't last long. It'll find its way back to the right process. So for the right applications, I think this technology really offers unbeatable economics. Material properties are excellent. It's fully dense. It's pressure tight. It's a unique combination of high elasticity, strength, and hardness. We've done parts for precision optics, surface finish quality. It's corrosion resistant. We've done salt spray testing to ASTM standards that have gone on for in excess of 300 hours with no evidence of any corrosion. It's scratch resistant. That's on uncoated surfaces, which make it unique. And this coefficient of restitution is just extraordinary. That's why the golf industry's been interested in it. It's supposed to hit balls further. I'm not a golfer, but I understand that's one of its many attributes. And it really makes a lot of complex metal component applications possible. It's like metal injection molding, it's volume ratio efficiency and shape. The first part of that, the volume ratio efficiency, is significant. When you're comparing that to machining, in this particular case, this geometry consumes only 9% of that block of material. If you were to machine it, of course, you'd have lots of waste. On the flip side, this is a great example where the LiquidMetal technology can do something metal injection molding cannot do very readily, and that's unsupported surface extended arms on the part, where you would get distortion, dimensional loss, and tolerance loss during demining and sintering. So this is my version of a table I put together actually Sunday morning at home before coming here. So it's not on your CD, but we'll certainly give you a copy of it if you're interested. I'm just trying to compare on several attributes LiquidMetal to die casting, metal injection molding, investment casting, and machining. So the big upside is low cost for high part complexity, fine surface finish, high elastic limit. It's 2% strain, which is just remarkable compared to all of these other metal processing technologies. It's a single processing step. You might argue, like die casting, you're going to remove the gate and the runner system as a second step, but it all happens at the molding machine. There's no heat treating required to achieve high hardness, and there's a side effect of heat treating, of course, with MIM, investment casting, and machining. You can get residual stress that comes from heat treating, which is a source of losing dimensional tolerance capability. So again, it's a real nice attribute to the process. We don't have any of those post-molding processes that can take away tolerances we've worked so hard to try to achieve. There's no heat treating required to get to the high strength levels. It's just a virtue of the technology. It comes along with the ride. Low scrap rate and tolerance control is quite tight. And I was somewhat generous here in that we have done much more precision work than I've illustrated at plus or minus 0.1% of a feature size. We have a couple components that we can share with you at our table that have been produced recently where the tolerance control is about half of that. And when I say I'm comparing that to machining at about the equivalent tolerance, I'm talking about high volume production machining processes, not tool making capabilities, which of course would be much more precise. Rather than fight another video, I'll just jump to my last slide. Thank you for listening and the opportunity, Mark, to present today.
Thanks, Paul.